Hello, I'm Mike McCulloch. So a couple of days ago, I was talking to you about the Allais effect, which I was proposing was an effect on a very low acceleration plane of a pendulum caused by changes in its environment very far away, so the sun and the moon, and that this was having an effect on the pendulum during eclipses while the moon covered the sun. So somebody in the questions asked in the comments, they asked a question about whether it would be possible to test this in a lab. And I did propose something like that way back in 2010, which is similar. So, and I have already made a video on that. So the idea was to use the particle accelerator of CERN to accelerate electrons or some other particle to a very high speed, and as it's going around a circle, it would have a very high acceleration, so that the Unruh waves it would see, and that according to quantized inertia cause its inertial mass, would be short enough to be affected by man-made electromagnetic waves that could be fired at these particles. Well, this question reminded me of another proposal I made in my book in 2014. So this book here, Physics from the Edge, page 122, in which, well, I noted an email I'd got from a chap called David Iannuzzi, who'd read my proposal for the CERN experiment and has suggested something slightly easier, a desktop experiment using what are called NEMs, NEMS, which are Nano-Electro-Mechanical Systems. So effectively, they're very small nano pendulums that oscillate incredibly fast because they're very light. The great thing about them is that you can get accelerations up to about 4 times 10 to the 11 meters per second, a huge acceleration. So it's not quite as high as electrons in capacitors, for example, which is about 10 to the 19, but it's pretty high. And the great thing about having high accelerations in quantized inertia is that the higher the acceleration, the shorter the Unruh waves the object sees become. So for this NEMS, this very small oscillator, you should start to see Unruh waves of about 10 to the 6 meters in length, so about 1,000 kilometers, which seems like a lot, but that's the Unruh wave being seen by the pendulum as it accelerates. So what if we could fire a similar electromagnetic wave at it that would interfere with the Unruh wave it's seeing and that causes its inertial mass? Well, then its inertial mass would dissipate. We could modify its inertial mass, and goodness knows what would happen to the pendulum then. So this is certainly possible, because waves of this length, so 1,000 kilometers, can actually be made by pigs. So I'm not referring to the animal here. I'm referring to pipeline inspection gauges, which can produce very extremely low frequency radiation like this, and there are certain other ways to do it as well. So if you had one of these things, how much energy would you have to fire at the pendulum? Well, the mass of the pendulum is something like 10 to the minus 16 kilograms, so they're incredibly light. So using E equals mc squared, you can work out the amount of energy that this represents, and this gives us an order of magnitude to work out how much energy must be directed at the pendulum to vary its inertial mass, and it's about 16 joules. So if you could get these long waves, fire them at the pendulum, this NEMS pendulum, very small one, then you should be able to detect some changes in its dynamics, and this would be a nice test book, desktop test of QI. So this is getting controversial again, but this always reminds me also of the wild experiments of John Hutchison in Canada, who claimed to be able to affect the inertial mass of objects by firing electromagnetic waves at them. and I think some of his experiments now have been discredited, but the core of them may remain. The early ones may still be valid. Okay, so I hope you've enjoyed this short, and I look forward to making another one for you tomorrow. Goodbye.